Let's find the volume of a solid obtained by rotating about the y-axis, the region between the curve y squared equals x, y equals x cubed, and we're going to use the shell method. And first we're going to find the points of intersection. And we're really only interested in the first quadrant here. So because the intersection will take place here in the first quadrant, we're going to take y squared and solve for x. Well, y squared, if you take the square root of both sides, you get y equals plus or minus x. But in the first quadrant, we're only interested in the positive solution. So y equals the square root of x. To find the points of intersection, let's let y squared equal y squared. That's the easiest way to do it. So we'll square the x cubed and get x to the 6th. So we have x is equal to x6 when we let y squared equals y squared. Solving for x, we get x equals 0 and x equals 1. Thus the points of intersection are the ordered pairs 0, 0, and 1, 1 when we find the y partners to these x values. The next step is to sketch what this thing looks like, the region that's enclosed by these curves. So first we'll do the y-axis, which is our axis of rotation as it was previously, and our x-axis. And we have the upper curve actually represents y equals x to the 1/2. We'll call that y upper. And the lower curve, YL, is the curve y equals x to the 3rd power. And this is where they intersect in the second quadrant. And I'm sorry, the first quadrant. It's actually the only two places that they intersect, these 2 points, 0, 0, and 1, 1. Now we're going to draw the approximating rectangle parallel to the axis of rotation. So that gives us a thick delta x, which indicates we're going to use a differential dx. Here's the sketch of what it's going to look like when we rotate about the y-axis. The radius of this shell is r equals the x value. And for the height, that's step 3, finding the shell height. We're going to find that in terms of x, of course, because we're going to be integrating with the differential dx. We can do a quick sketch here to see what this thing looks like. The approximating rectangle represents the height. The height will be it's actually the height would be the upper minus the lower function. And that would be y upper minus y lower. So it's x to the 1/2. It's going to be x to the 1/2 minus x to the 3rd power. And you can see that in the sketch, that is the overall height of the approximating rectangle. Step 4, we'll use the formula for the volume again when we're rotating about the vertical axis, the y-axis. V equals the integral from x equals a to b of 2 pi times x times the height f of x dx. So in this case we have the integral from 0 to 1, 2 pi times the radius x. That's the width. If we had cut open the shell and spread it out, that's the width. And then the height is the difference between the y values, x to the 1/2 minus x to the 3rd dx. Now as we continue, you'll recognize that this is very similar to finding areas between two curves, because indeed we are finding the area between the curve, and then we're rotating that region, that area, around the axis of rotation. That's why it's so similar when it comes to things like y upper minus y lower. Okay, so we continue evaluating and we get 2 pi over 5 times 2x to the 5 halves minus x to the 5th. That's the antiderivative. Evaluate, simplify, you get 2 pi over 5.